Hello, folks. My name is Bryce Gernon, and today I'm going to be giving you a brief overview of some of my theory work in using graph traversal to do better deepfake detection model training. So, quick overview of some of the background work. First of all, deepfakes. What are they? They're an image or video manipulation where you are swapping someone's face with another, puppeting a facial face with someone else's facial movements, anything that is manipulating that face, right? So it's got a couple positive uses, movie CGI, art, that kind of thing, but a lot of negative uses, blackmailing, non-consensual pornography, a lot of political deepfakes, especially this time of year, and also political deepfakes for usage in like the Ukraine war, for instance, where both the Ukrainian president and the Russian president were deepfaked. And it can be very, very difficult to tell what is a deepfake and what is real. So look at these two. Which one do you think is fake? All right. So on the left, we've got one that, we've got a head tilt there, but the face appears to be a little more straight on. So that seems kind of weird. But on the right, it seems like the top of the forehead is blurred somewhat, and the glasses, they seem like a little bit too clear. Like you can't really, see any edges or all at all. So what's going on there? What's the video artifacting? What's air lighting? What's the actual deepfake? What do you think? Well, turns out I've tricked you, positively bamboozled. Yeah, you see, they're both fake, and they're both from the face forensics data set. Um, but this is sort of to showcase not only is it really difficult to detect what exactly is a deepfake and what's real, it can also vary a lot depending on the exact deepfake method that was used to generate them. So generalization and overfitting is a really big problem when we're training our detection models, because deepfake detectors that are trained on a single data set tend to overfit on that data set and on the methods present in it, and they perform very, very poorly on other types of deepfakes and just other data sets in general. And training on multiple data sets and deepfake types is possible, but it tends to result in a lower accuracy because you just have a lot more classes, like the deepfake classes, to go over. It's a much more difficult problem. And then you still have some generalization problems when you're applying it to unseen data. And not only that, but there's a significant issue with balancing the volume of data and the variety of data. So if you have 100,000 deepfakes of type A and 10,000 deepfakes of type B, what do you do? Do you just take 10,000 of each and ignore the fact that you're emitting 90,000 deepfakes that could be in the training set? Or do you take all the data and just use it all at once and, try to ignore the fact that your model is going to be terrible at detecting deepfakes of the second type because it's spending the vast majority of its time training on deepfakes of type 1. It's a real, real issue. And so improving the generalization capability of models is a key research area. So my proposal centers on the usage of graphs to do deepfake detection model training, right? The idea here is that we're going to convert deepfake data sets into a graph-based format. So we're going to take, if it's an image-based data set, we're going to take every image from it and turn it into a node. If it's a video-based data set, we'll either take one frame and turn it into a node, or a sample of frames and turn them into very close nodes. And then we will draw edges between each node that shares a given number of facial attributes. Now, what are these facial attributes? They can be a lot of different things. They can be deepfake generation methods. They can be race. They can be gender. They can be facial hair. They can be anything that we can get accurate labeling of, right? And the idea is that it would look something like this. So if you have four attributes, A1 through A4, your nodes are going to be generated and connected in such a way that A1 nodes can connect to any other node that has an A1 attribute, for instance. So you can see at the top left, A1 connects to A1, and then connects to nodes with attributes of A1, A2, A4, that sort of thing. And that slowly connects the rest of the graph. So eventually, if you follow enough hops down the graph, your A1 node will be connected to an A4 node. But that's because it is slowly traversing through all these shared attribute nodes. And the idea of this is to really provide some localized information. So we can say this area of the graph has faces that share these attributes. They may share similarity information. So if we have SSIM scores or something else that allows us to calculate similarity between faces, we can use those to get even more contextual information. And this can be used to create some really powerful localized information. And not only that, we can do subgraph extraction. So if we want to train a model on a very specific area of data or a specific distribution of data, we can point at a node and say, okay, we're going to take all 100 nodes, 10 hops out, 100 hops out from this node, get that subgraph, train some models on it. And we can also extract subgraphs that are one specific attribute or a combination of specific attributes. So, I only want to train on face swap, which is a deepfake generation face swap, nodes. You can take the subgraph of all nodes that have faces generated with FaceTime and train models on that. Now, admittedly, you could do that with a regular data set as well. But that's actually kind of one of the perks here is that we've got equivalence. So when we're generating this graph-based data set, we're not taking anything away from the original training methods because you can always go over the nodes in list-wise order, right? So node 1, node 2, node 3, node 4, regardless of the edges between them, to replicate standard training methods for comparison, right? But if we can leverage that contextual information between the nodes and control how we traverse that graph, we might be able to get some better things done, get some better training done. So really quick to explain how this traversal is going to work. This isn't a graph neural network. It's a standard neural network, or any sort of detection model that is deployed on a graph. So we would attach a pointer to the graph that's attached to a specific node, and we would move that pointer from node to node using some sort of traversal method, which I will get into shortly. And this will accumulate information within the pointer until we have a large enough batch to send to the model, at which point we then do training. We get all our predictions back and everything. We do optimization, loss scores, everything like that. Um, which is all well and good, but we need to do intelligent traversal. Since if we're randomly traversing on the graph, we may as well just randomly sample in data from the data set. We don't even need a graph at all, right? So the core concept behind this is that if we can intelligently traverse and carefully control the data set and the data that the model trains on, we'll be able to not only spend more time training on useful data or data that has a high value, whether that is data that is has some very specific feature that the model needs to know, or just something that the model hasn't spent a lot of time training on. So if the model has spent, say, 70% of its time training on face swap faces, we probably don't want it to be spending a lot more time training on that, at least right now, while that ratio is still 70%. So instead, we can direct it to start training more on faces from a different deepfake generation method. And the idea to actually quantify this and get a very strong automatic measure of the information of a node is to create a metric I which measures that informational value relative to the model that we're currently training. So this is based off of some reinforcement learning ideas. Essentially, the idea is that we can take the logits of the prediction and use them to calculate a sort of Q value, right, based off of a reward. So if the model is very confident in its prediction and it's accurate, high reward. If it's very confident in its prediction, not accurate, so it makes an incorrect prediction, low reward. And then if it's confident about its prediction, 50-50 basically, then it gets medium reward. And then we use that to generate our Q values using the Bellman equation, with the idea being that this counts the value of the current state plus future states, which in this case would be the current node plus nodes that we could get to from there, meaning adjacent nodes, right? So we're applying the discount factor. So this node we're at right now has some amount of informational value plus the informational value of an adjacent node times the discount factor, so on and so forth. And then our informational metric is essentially the negative of the Q value. We also add in some threshold terms, with the idea being that we don't want the model to just loop in a circle and only go to the same 2 or 3 nodes. So we add that threshold value. But other than that, it's really just the negative of the Q value. And the idea of that is that if we can figure out where the model will have very accurate predictions using some sort of deep Q network, and we have very confident predictions of that, then we can figure out where the model doesn't need to be training. Because we don't want to train more on areas where we have accurate predictions. We want to train on nodes where we don't have accurate predictions. So if we train a small reinforcement learning agent, the idea is to make this relatively fast. We can get the Q and I values. We'll be able to traverse 2 nodes that we do poor prediction on. And the idea is that we're going to automatically correct for any biases of the model that are biases on facial attributes that we have in the graph. So as it goes and trains more and more on certain attributes, it will learn to detect faces with those types of attributes better in terms of deepfake detection, at which point the I values for those nodes will decrease, and then it'll automatically spend more time training on other nodes. We can extend this, deepfake generation methods, facial attributes, bias, whole bunch of applications for this. So yeah, that's the general theory behind it. There's a lot more that I can do with this, and a lot more that I'm looking forward to researching. Specifically, how do we do fast predictions? Can we use convolutional DQM to extract more facial features? Is there a way to use enough facial attributes that we don't even need to use a DQM, and we can just do some sort of algorithmic approximation of the informational value? And also, what do different graphs look like when we're generating them out of different data sets? What is the best way to generate a graph that has the correct amount of information within those nodes? and how can we measure bias of models that are trained on attribute-specific subgraphs. So a lot of interesting work to do here. I'm looking forward to doing it, and I'd love to discuss with you on it if you are interested. So thank you for watching, and yeah, feel free to email me any questions that you have. Thank you.